how is Calc 3 different than Calc 1 and Calc 2? The easiest way to explain that is just to remind you what you did in Calcs 1 and 2 very quickly. Calc 1, you studied limits, and you use these limits to talk about derivatives and integrals and things like that. And so you would look at a function like this, y equals x squared, and you would ask a question like, what's the equation of the tangent line to this curve at a point? So, how did you do that? Well, let's pick this point right here at 1, 1. This is a very nice point. And let's find the equation of the tangent line. Just remind ourselves how to do it. Now, to do this, you need to remember there's a formula for the equation of any line whatsoever. And it looks like this. It's called the point-slope form of the equation of a line. Now, it's not the same as mx plus b, which is called the slope-intercept form, but it's something we can use. And in calculus, it's preferable because you don't need to know the y-intercept for this. We can just use this point 1, 1 that we're talking about here. And so we know this point, and so we know x0, y0, because that's 1, x0 is 1, and y0 is 1. So we will plug those into our equation, but no line appears because we have not yet added a slope. Now, how do we find the slope? Well, differential calculus, which was what you did after limits, was about this question. How do you find the slope of the tangent line? Well, you take the derivative, and then you plug your point into it. Now, in this case, the derivative of x squared is 2x, and so it only has an x in it, so we'll just plug the 1 into that, and we'll get 2 for the slope. As derivative is 2x, I'm plugging in x equals 1, I get 2 after I do that calculation. And I put the slope in, and if the theory is correct, I should have a tangent line appear right now. And there it is. I don't like their color scheme, but that's okay. It's Halloween. Now, what you did after derivatives is you looked at, how do you use this to do various things, optimize functions, things like this. Eventually, you switch gears, and you ask a different question than the tangent line question. You ask the area question. And that's the question of, if I have this curve, this orange parabola, and I want to know the area under it, how do I do that? And you ended up with 2 answers in Calc 2 to this question. One answer was, well, the way you find the area is you draw these little rectangles, and I'm not going to draw them here, and you fill them under the curve and above the area you care about, and then you shrink the width of the rectangles to get a better approximation to the area, and then you take a limit as the width of the rectangles goes to 0, and out magically pops your number that you're going to call the area under the curve. And that's a very geometrical approach, but it's it involves an infinite process, and so computing it by hand especially, or even with a computer, is not exactly feasible without a theory to do it and define it in many steps. And that's where Calc 1 punches you in the nose and says, aha, we can actually do this with antiderivatives, which brings Calc 1 to sort of a full circle where derivatives and integrals are actually the sort of two different sides of the same coin. Now, that's where Calc 1 ends. Calc 2, you kind of just, it sort of feels like you do a lot of tricks to compute these integrals and apply them to things. But the memory that most people I know have of Calc 2 is that they remember integration by parts, and they remember trig substitution, and it was just a lot of random things about integrals until they got to sequences and series, and then the whole sort of focus of the course switches gears, and you study infinite sums and things like this. And so Calc 2 always kind of feels a little awkward in that sense of your integrals are building up to something, and then you switch gears completely to series, and that leaves you wondering, well, what on earth are we doing in Calc 3? Because, we switch gears so hard in Calc 2 to something that feels foreign, although it was connected to derivatives and integrals, be like Taylor series and things like that, but still, I don't know, had a different flavor. Calc 3 is not a continuation of sort of that track of thinking. Calc 3 is more of a back to basics kind of approach to calculus, in the sense of, well, we are going to study limits in here, but we're not going to study them in more formality, but we're going to study them in a broader context. And that broader context will be multiple dimensions. Now, I mean, obviously in this picture here, we're talking about 2 dimensions. I have left, right, I have up, down, and that's it. In this actual mathematical world of these derivatives and things. And we will do a lot in 2 dimensions, don't get me wrong. But Calc 3 is the idea that these basic ideas of derivatives and integrals actually generalize to multiple dimensions in a nice, elegant way. Now, is this just abstraction for pure abstraction? I mean, when I hear the word dimension, I'm thinking in popular culture, it's some kind of alien thing, maybe, I don't know. But it's not that. Dimension is just a number we give to talk about, in the context of what we're talking about, how many things we're tracking. So if I'm tracking my position in a room, I'm going to use 3 dimensions, because I could go forward, backwards, left or right, up and down. And up and down are negatives of each other, right? So there's really 3 fundamental directions. In a linear algebra course, you would call them 3 basis vectors. But, we kind of think of them as just the 3 possible directions we can move in. And so what would be 4-dimensional? Well, you could build your reality around you into 4 dimensions by just, the popular thing to say is time, as time goes on, but it doesn't have to be time. You could have a system modeling your position in a room, and then the 4th thing you're tracking isn't maybe the time, but maybe it's the temperature in your body or something. So maybe you're getting a fever, and you want to know, as I walk around and do my daily routine, is my fever getting worse or better? Maybe you shouldn't be working if you have a fever, but you see what I'm saying. It's just dimension is just a question of how many things you're tracking. So if I'm a company and I want to track, all the things that I manufacture and how well they sell, which markets that this research went to versus this research, and all this, you can see that any system worth studying in depth is multidimensional to its core. The more things you consider, the better your model will be. And so Calc 3 is the extension of questions like, how do I optimize the curve to find the minimum, but to multiple dimensions? So you can apply this idea of minimizing a function, whatever it means. Your function could mean the profit with taking into consideration the price of my inputs, the tariffs on the country I'm shipping it to, and the labor cost in my company. And you can add more and more and more things, and that increases your dimension. The techniques we learn in Calc 3 generalize to multiple dimensions very nicely. And so you'll understand how to kind of go anywhere with calculus that you want. Now this will take a few shapes. So for example, what are integrals like in multiple dimensions? Well, in 1 dimension you have these rectangles I mentioned, and then in a higher dimension, instead of being under a curve, you're going to be under a surface. So sort of imagine like a bed sheet, and you're holding it in the air, and you want to know how much area is under this thing. But one way you could do that is to, instead of building rectangles, you could build little pillars. That's this thing. And you could measure their volume using length times width times height, area of a rectangular prism, and add them up. And then you shrink the prisms, and you will get, a nice area under this curve. So geometrically, you should feel how similar that is to area under a curve, volume under a surface. Very similar kind of question. So Calc 3 is filled with interesting looking pictures like this. This is what we call the modulus of the gamma function, which is a very special function of two real variables that serves many useful purposes in mathematics. And in fact, what it actually is used for quite often is for giving a meaning to factorials of non-integer numbers. So remember, factorials are this function that multiplies by itself minus 1 all the time. So like 3 factorial is 3 times 2 times 1, which is 6. Or 4 factorial is 4 times 3 times 2 times 1, which is 24. And this function gives a meaning to a question like, well, what's 1/2 factorial? And you can go look what its value is up yourself. But that's the gamma function, and it's a function of two real variables, this horizontal variable and this vertical variable. And these, what's going on here? Well, these are places where this function blows up. So this is like, how y equals 1 over x, which I guess I can plot, blows up at 0. If you zoom out, this function has asymptotes at 0, and from the right it goes up, from the left it goes down. This function, by its definition, it is always non-negative, and so these things always go up. Though if you look at a sort of slight variant on this picture, you can get ones that go down as well. And it's very interesting. It's a nice looking picture. Now it looks kind of old, and that's because, well, this is from the 50s. This is an old picture from a book that's now in the public domain, called Abramowitz and Stiga. Anyway, so we will study, objects that look like this. They're three-dimensional. They're landscapes you can kind of think of. But these are only functions in 3D. When we get to higher dimensions, we can't really visualize it. So what kind of thing would you do with a function like this? So here's a more modern kind of plotter. What is being plotted here is this equation, z equals something. So the fact that we have 3 variables means we're tracking 3 things, and so we have a function in space is what we could call it. And if I'm, say, at the peak of this surface, wherever that is, if we're talking about doing Calc 1 over again in upper dimensions, well, what on earth does that mean? Does that mean I want to find like the tangent line at the top of this? Well, kind of. At the top of this, you can imagine placing a tangent line that kind of goes like this and is at the peak. But you can also imagine placing one doing kind of like this. And I should have drew them, but I didn't. But the point is you can have multiple tangent lines in multiple different directions. And so what you end up getting is, instead of a tangent line, you get a tangent plane. And so you see that this object is sort of linear. It's made out of straight lines, all parallel to each other. And it's resting exactly touching one point of this curve, like the tangent line did earlier to that function x squared. So this will be the Calc 3 sort of analog of tangent lines in 3 dimensions. If we're up in higher dimensions, again, we can't visualize these things very nicely. There are ways, but to visualize a few dimensions, but at some point you kind of can't. And what are the planes in these dimensions? Oh, you call them hyperplanes or something, but it doesn't really matter to us what we call them. What does matter to us is that we can find them and use them for things. So that's how derivatives sort of will evolve later in this class. And finally, the end of the class, we end up with these kind of objects. Now, these are called vectors, and we will soon have a whole chapter about vectors. But what's going on here is we have a bunch of arrows in the plane, and they are pointing in a certain direction, and they are a certain length, and that's what vectors in this Calc 3 sense will mean to us. Those who've had linear algebra have seen vectors before, and maybe you've seen them in a few different ways. And we will mostly think of them as these arrows, but we will compute with them using coordinates and things. So, this is very common in a linear algebra course, but it's just as easy to learn it here and use it. So we won't be studying vector spaces. That's what linear algebra ends up doing, okay? But we'll use a matrix here or there, but we really aren't focused on these topics in Calc 3. Calc 3, instead, we're interested in how we can use this along with calculus-like techniques. And the best I can tell you right now is that we'll study things like this cycle over here, and how this cycle is different in some sense than these other places. Or, if I dropped, what is this telling me? If I dropped like a piece of dust, and this is representing wind, let's say. If I dropped a piece of dust right here, these arrows are suggesting to me that the dust will be blown towards the origin. And the arrow here is suggesting if I drop something here, it will be also blown to the origin. So if I'm at the origin, the up and down seems to suggest that I'll stay in place. And the left and right, it's not really clear exactly what happens here, but it sort of looks like if the dust particle wandered this way, it would be blown sort of into this cyclone. But if it was blown this way, it would sort of been blown away to the negative real axis direction. So how that interacts with calculus is not very clear yet, but it will become clear later. It ends up being a very nice unifying concept among this tangent plane concept and this area under a surface concept. So this is a picture that I took from a wind map that I think still runs, and it was in 2012 during Hurricane Sandy. And this is an example of this sort of vector field, because at every point, now this is just a still image. The actual website was moving when I took the picture, but it's showing you, the direction of the wind at all points in the U.S. It's obviously collected by weather stations or something, and it draws the wind everywhere. And so during the hurricane, you could see the wind getting sucked into the vortex of the eye of the storm from Chicago all the way to New Jersey, New York. And this is a great example of a vector field. Now, where does the calculus come in? Well, the vector field itself is sort of an algebraic object in the sense of, when you know if it has a formula, which it likely doesn't in a real-world situation, but you can do algebra with it. The calculus would be a question of, how strong is this suction action going on at the eye of the storm with this wind? Can we measure that? Questions like this. So, we'll be able to measure things that it'd be hard to measure with a single variable, because there's speed and there's direction, both interacting and being important in this scenario, just like the dust here. If I was slightly to the right or slightly to the left, very different in behavior. So, Calc 3 is sort of a meditation on these three things. We have the area, the volume under a surface. We have tangent planes and things you can do with that, which will include multiple variable optimization, things like this. And then at the end of the course, we start talking about vector fields like this and how it serves as sort of a unifying perspective on derivatives and integrals, just as the fundamental theorem of calculus in Calc 1 serve to unify integration and differentiation. So, in short, Calc 3 is Calc 1 all over again in higher dimensions.